today we will discuss about how to design a heater drive for various controllers, because we had seen already how to use on off temperature controller and then proportional and PID temperature controllers, but we have not discussed in detail how to design the heater drive. So, for 2 minutes I will explain for on off controller how it is to be done, then I will explain how we have to do for proportional or PI or PID temperature controllers, the heater drive part. So, we will discuss about the heater drive part. For on off controller, first I can briefly explain for on off controller what is to be done. For on off controller, the heater either should be switched on or off. So, we can easily do. For example, if I have the final stage of controller, one is given to the V reference, other one is the sensor voltage. So, you have a comparator. So, I will pick up the thread from the comparator output. So, if heater to be on, it will be plus 15 volt, and if it is minus 15 volt, it should be off. So, we pick up from this point. So, the on off temperature controller, if it is plus 15, heater to be on, minus 15, heater to be off. Now, for low power, of course, the easiest thing would be I can connect this through a driver like this. So, I can have this and then I give a plus 15 volt, and then if the power level is high, then I can do the improved version of this. For example, I can have a plus 15, this is we have put a Darlington pair. So, when it goes plus 15, this will be 14.4 and that will be 13.8 volt. So, it will be on. When it comes minus 15, that you get 0 volt here and heater will be off. To make it to discharge the storage charge, we can have one resistance maybe around 10K to discharge storage charge, that serves the purpose here. So, put this, that becomes alright. So, the Darlington pair can be used for high power current, because the current in the base cannot be more than 10 milliampere, because most of the op amp rated for 10 milliampere output current. So, in this case, if the HFE of this is say 100, then 10 milliampere 1 ampere current can go through this, and the transistor should withstand that much power, that much heat, because anyway it is on time, about 1 volt is there and about 1 watt heat dissipation will be there when 1 ampere current is flowing. In this case, for high current, then we can have a Darlington. For example, this can be 3055 and this can be 3019. So, 10 milliampere here can become 1 ampere here per HFE of 100, and high power transistor HFE is low, that is 20, then up to 20 ampere current can go through this, provided we put a heat sink for this transistor. We had discussed about the heat sink design in our earlier lecture. The same thing can be used here. Now, other possibility of on off temperature controller drive would be we can have the same for example, I pick up from the comparator. So, you have this. Now, I can have a relay and then switch on and off. This also we had discussed earlier. So, you have a plus 15 volt and then you have the relay here, and then the relay can power the whatever circuit you want, either AC or DC can be used. But as we said, the relay life is a mechanical object. So, what happens whenever contact is made and broken, then some part of metal is lost here, and then the number of times it can be operated get reduced. So, for very frequent on off this is not suitable, but this can operate either AC or DC or high power, it can be used. Suppose if you have a DC of high voltage, then the on off controller also can be used like this. So, you have this controller part leaving, then for example, I can have the on off part can be like this. Then if you want, I can also have a Darlington, and then here it can be even connected to high voltage, say 100 volt or 300 volt, whatever it is DC, and then I can have this. So, this can be a heater and this can be high voltage and high power, because now the even 15 volt what is coming here can switch on this, and this voltage can be even 300 volt or even any amount of voltage. Only the condition is that this transistor and this transistor, this and this should withstand a VCO breakdown, then only this can work. So, this is easier to write, or we can also use for example thyristor. So, in case of thyristor, what we can do is we can have a drive and then we have to fire the thyristor. Now, thyristor has to be isolated. The easiest way of doing this would be use opto isolator. For example, I can have the, so whenever this is plus 15, then it diode allows this plus 15 to come. So, you will have 14.4, and then optocoupler needs around 2 volt, this is LED of the optocoupler. So, the light glows. So, we have to limit the current by 8 milliampere. So, most of the LEDs take 8 milliampere current. So, the resistance R required will be if you have around 4 because this normally if you are operating plus 15 minus 15 minus 15 volt, you may get around 14 volt, then here around 13.4 volt and 2 volt gone. So, 13.4 minus 2 volt is the voltage across the resistance. Because taking this as 14 volt and this as 0.6 volt, voltage across this 0.6 and 14, that you arrive at 13.4, this point you arrive at roughly 2. So, that comes 11.4 volt across resistance, that is a voltage across the resistance. So, for 8 milliampere current R will be 11.4 divided by 8 milliampere, that will be this. So, that is roughly about 1.5 K. So, the 1.5 K resistance put here, I will see that whenever the suppose heater on, this will go plus 15 volt and the LED will glow with 8 milliampere current. Now, other side we can have the optocoupler. Basically, this is optocoupler with transistor one side and the LED in the other side. So, this optocoupler whenever it is high, the optocoupler will be conducting. So, I can have a resistance here and this ground will be different ground. So, I can have a thyristor here, a triac for that matter. If it is AC, you can have a triac, and whenever this is high, the triac can fire this. So, you have a AC current here and then the load connected here, and that is connected at this point. So, that is the load. So, AC you have and the current goes through this. So, whenever the LED glows, so this is supposed to have isolated supply plus 15 and that current 0 of the plus 15 supposed to be here. So, this supply is connected here between this point and this point. So, essentially when the LED glows, this conducts and this voltage goes high and that fires the gate of the triac. So, that the gate conducts, and whenever the LED off, this will come 0 and the triac will not fire this one. Now, this is a very rudimentary circuit. This can be improved by putting a Darlington pair because the current required to be seen. So, if I redraw the drive part of the triac, that you have this and then you have the load and then you have the triac. So, if this is plus 15 volt and have this, I can improve this by putting a current, because I want to push the current and can give this, and then to avoid dV by dt failure I can connect on resistance like this. So that when this is off, this is not floating and that is connected to ground, and so that the dV by dt triggering is improved, the noise triggering will not be there. So this is one possibility. So here is this is acting as a load, and then this side is our LED. This is the up isolator part. So this ground is our circuit ground, the op amp ground, side ground, and this side is the power ground. This and this are no way connected. So you get the total isolation because this ground is different from this ground. So there is no shock hazard for the user of the instrument, and this 15 volt supply is different from the 15 volt supply used in the analog side. That should be different, otherwise you will not get the isolation. So this plus 15 is different from this. Now the circuit also further improved in the sense that we can make the triac to fire only at zero crossing. That is also possible. That we will discuss probably in the other part, that is in the when we are using a drive for proportional controller. So for on off controller, these are the different possibilities of driving the heater voltage. This is mainly to practice the formation of different circuits, because one have to acquire the circuit design skill only in a smaller steps by seeing how each step is followed. Now let us see next how to design a heater drive for proportional controller. So next we see heater drive for P or PI or PD or PID, all are same because output voltage is to be linearly varying, with the error. So it is not more on off because what you have discussed so far are on off, you had either switch on or off, that was quite easy. But now the same thing whatever we had seen there to be implemented for proportional action. That is we see for example a simpler case where a smaller power, like for example crystal ovens are there, they need only 1 or 2 watts of power, mostly they operated at 15 volt. If I want to design a PID temperature controller for a crystal oven, then I will, as I discussed, you may have you will have a PI stage or PID stage, whatever it is, and then the output of that will give you analog voltage proportional to the error. So that error voltage, I assume that I am getting it here. So that is the error voltage that you are getting, which we have discussed earlier classes. So the error voltage must drive a heater. The error voltage must be proportional to the heater voltage. So here in this case, when positive is there, it is supposed to go. So I can have the diode to block this, and then I can have this, and this can be connected to plus 15 volt. So that whatever voltage is here at this point, the same voltage minus 0.6 ampere. Suppose if it is a 10 volt, then you will get 9.4 here. So when error voltage increases, this voltage also increases. So heater voltage increases linearly. So this system works. Of course this current can be maximum only 10 milliampere. So this current cannot be more than if it is HFE is 100, then this current cannot be more than 1 ampere. But then here, unlike on off temperature controller where the voltage drop is very small, only the device is either on or off, but here it is neither on nor off. So if it is 5 volt, then this will be 4.4. So voltage across this will be 10.6 volt. So this, if 1 ampere current goes, then there will be a 10 watt heat dissipation, which will be enormous. So this transistor should withstand all the high power. So one improvement that can be done is we can, instead of having the simple thing, we can have high power device at the output. So I can have the same thing with the Darlington. You can have a Darlington and the heater. So here this current is multiplied by 100 times beta of this, suppose here it can be maximum 10 milliampere current, means up to 1 ampere current can come, and this can stand up, take up to 20 ampere current, because HFE of this high power transistor is only 20, that range. For example, 3055 if we take, HFE is only 20. So, we can have a heater drive like this, which can give high power, and then this also can dissipate high amount of heat, and heat sink can be utilized for this purpose. Now, this kind of heater drive works only for very low voltage, that is up to 15 volt, because if this is 15 volt, then this can go only 15 here, 14.4, 14.4 minus 0.6 will be 13.8, minus 0.6 will come to 13.2. So, heater voltage cannot go more than 13.2. For example, I cannot have a heater drive like this to drive high voltage. For example, I cannot have this. Like what we have done in the on off controller. So, I can put this drive and I put this. So, for example, here plus 300 volt I put, and then put this and then put this. This will not work, because what will happen is that if this voltage increases linearly, this voltage across this will not increase linearly. This is a major problem, because we want, if this increases, this voltage across, the error voltage increases, voltage across this heater should increase linearly. That will not happen in this circuit. So, if you want that to happen, then we have to modify this circuit. Now, one simplest way of modifying this would be, we can have a I pick up the thread from the output of the error amplifier. Then, for example, one simplest way could be, I can have this, I can have this, have a resistance here, then have a heater here. In this circuit, we had used this resistance. Assume this base current is negligible. If the base current is negligible, then I can assume there is no voltage drop here, and if, for example, if 14 volt is present at this point, we know at this point you will have 14 minus 1.2, that will be 12.8. So, current through this now determined by this 12.8 divided by this resistance. Now, since this current is same as this current, assuming this current negligible, I can take this and this are essentially same. So, in that case, when the voltage increases here, this voltage increases, this current increases, this current also will increase. So, this way, when the voltage at this point increases linearly, voltage at this point increases linearly. So, the current through this also, and then so the current through this, that means voltage across the heater will vary linearly with the error voltage. Now, of course, this ratio between these two gives you the gain. For example, take, for example, I have a heater resistance of 100 ohms. If the heater voltage needed is 300 volt, then I know 300 volt and around 3 ampere current is what is needed, that you have to go through this. So, other way around, 300 voltage you have to come when, say, for example, when voltage at this point is 10 volt. So, 10 volt has to become 300 volt, that means you need a gain of 30, that means this resistance and this resistance should have a ratio of 30, that means 100 by 30, this is 100 ohm, and the gain requirement is 30. So, we need 3.3 ohms. For example, I put 3.3 ohms, 3.3 ohms if I keep this, because when the voltage at this point changes by 10 volt, I want this heater voltage change by 300 volt. That is why we are calling gain of 330. So, 10 volt change you have to produce a 300 volt change here. So, that can be achieved by keeping this resistance ratio as, this is 100 ohm. So, I put 3.3, that is the ratio of the resistance 300. So, when the voltage across this 1 volt, obviously voltage across this will be 30 volt. So, like that when the voltage increases here, this voltage increases and voltage across this also increases. So, that it linearly goes up, but this will not work when the error voltage is very small. For example, if the error voltage is 1 volt, then this voltage is almost negligible and almost 0 current flows. So, there will be a nonlinearity issue in this case. And added to that, there will be a large power dissipation across this, and 300 volt is there, and if only about 100 volt is present here, remaining 200 volt will be across this, and that will produce a very large heat. But nevertheless, if it is can also be used, or if you want to avoid this small problem that you are facing with this, still this circuit can be improved in the following manner. What I can do is I can take the error voltage from here, and then what I can do is the error voltage can be further compared with another comparator, and that can act like a voltage regulator. Like for example, I can have the here 300 volt fitting. This is like a high voltage power supply. So, I can have this. This can be utilized to drive the high power. So, we can have the output voltage coming here, and this can be fed back to with a division 1:30. For example, I can divide this a voltage regulator and give it to this. So, idea is if I know that if the input voltage, this is say if I have a 10 volt, 10 volt should produce a 300 volt, this is a heater. So, the 10 volts should produce a 300 volt across the heater. If it is 1 volt, I want 30 volt across this. If it is 2 volt, I want 60 volt across this. Now, here what it does, we are given this 300 volt here between this and this, what we are given is this 300 volt is given here. So, what is done is this 300 volt whatever is coming, I divide this using a voltage divider and give this as a reference. So, if this is 10 volt, if this is 10 volt and if this is less than 10, if this is less than 10, then output will be almost 0 or minus, then this will be off. If this is off, if this is 300, this also will be 300, and then you will get almost 300 volt, and the heater will be getting 300 volt. So, because of that, heater voltage high, now this voltage also will go high, and if this goes high, automatically this will come down. Suppose if this is 10 and if this goes more than 10, if more than 10 means this, assume that this is as a division of 1:30, that is at 300 you will get 10 here. So, if I give 10 and this, if it is goes more than 10, then this will go high and then this will conduct heavily, and this voltage will come down because the current flowing through this produces a voltage drop. So, then voltage across this will be reducing. So, when this is high, then voltage across this is reducing and output also reducing, and that automatically reduce this. In case if this goes below 10, then automatically this will go minus, and it will other way around, it will go reduce, and this will go high and this will go high. So, whatever voltage is here, 10 volt means this also will come 10 volt, if this 1 volt, this also will come to 1 volt, 2 volt means this also will come to 2 volt, and then correspondingly this also will increase. If it is 1 volt, then this will be 30 volt, 2 volt means 60 volt. So, now this will linearly increase. Of course, the loop will oscillate, and we have to put the loop stabilization network to stop the oscillation, but nevertheless this can be achieved by doing like this. But this will solve the problem what I told you in the earlier case, that is at lower voltages, that is like error voltage is small, you may not get the output voltage, that problem is solved, but still there will be a large heat dissipation on this transistor, that problem is not solved. We can solve that by using a PWM control for this. Like what I can do is that if this is the error voltage, if this is the error amplifier's output, so here you get voltage corresponding to the error. Now, this can be this is to be this voltage, you have to drive a heater proportional to this voltage. At the same time, we do not want the transistor that the transistor which is driving heat it up too much, because it happens in high power cases. So we can go for pulse width modulation technique. So using pulse width at a C, pulse width modulation technique, how to reduce the heat dissipation. So what you do is, in this case what I will take say a MOSFET as a switch. So N channel MOSFET I have taken, and then source I ground it, and then I get the gate I have, then I have the drain here. So I put the load here, then my supply, power supply, I connect it here. So the idea is that this is coming as a, this is the heater actually. So what you do is, this is a heater. So what is required is the power dissipated across this heater must be proportional to the error voltage here. That is what we want. We do not want switch on off like what we have done in the on off controller, but we want this voltage and the heater voltage must be proportional, or other way around, power dissipated on this must be proportional to the heater voltage. So what we do is, if I switch on, it will be fully on and 300 volt will be across this, and only very small voltage across the MOSFET. Then if I off, then all voltage across this and no current is flowing through this. That way the MOSFET will not get heated up, because during on time only small voltage is there, during off time there is no current. So heat dissipation will be less if I go for on off mode. Only problem is that we have to convert this voltage into pulse width. That is the thing that is to be done. That we can do using a simple circuit, like for example, I can have a I can compare, for example, I produce one triangle wave or a sawtooth wave at this point, then I can connect this to the other one. So this point is given to the sawtooth wave generator. We will see how to generate sawtooth wave. We can have this, and that is what it is given here. Now to switch on the MOSFET, I would give plus 15, and switch off, I should discharge the gate source capacitor, then the MOSFET will go off. So first let us see how to switch on. I can do this, switch on, and I put on resistance to discharge the gate source capacitor here. So if this is plus 15, then MOSFET will get 14.4 at the gate, and that is much more than the threshold voltage required per MOSFET. So the MOSFET will turn on. So initially, for example, if the if this voltage is small, for example, if it is only 1 volt, then the sawtooth is rising. So when it is below 1, that is the sawtooth voltage is when it goes more than 1, because you have a sawtooth voltage going from, this is 0, this is plus 15. Then if the error voltage whatever we have here, if it is more than say it is 1 volt, then the 1 volt is here. If this voltage is below 1, this is high, because this is say it starts from 0. Once it goes above 1, then this will go high. Or I can do other way around, then I can change the polarity of this, that would be easier. I do one thing, I remove this plus and minus, I put the minus here and plus here. So in this case, initially when this voltage is 1 volt and when the sawtooth starts at 0, so up to this sawtooth reaching 1 volt, output will be high, then heat will be on. Suppose if this error voltage is 5 volt, if the error voltage is 5 volt, error voltage is 5, then sawtooth takes time to reach 5, but only when the sawtooth reaches 5 output will turn negative. So, still sawtooth reaching 5, the sawtooth has to go to 5 volt, it is 5 volt. So, sawtooth slowly rises and reaches 5 volt. So, up to sawtooth reaching 5, this will be plus. So, output heater will be on. That means it will be on for more time. Suppose if the error voltage is 10, then sawtooth the output will be minus, still sawtooth reaches 10 volt, that means output will be more volt, that is output will be initially plus, because this is higher 5 volt and this starts from 0. Only when this point goes more than 5, output will turn negative and it will switch off. So, now the on time was proportional to the error voltage. So, what is happening is on time is proportional to error voltage in this arrangement. So, error voltage is given at this point and fixed sawtooth is given. So, that way the heater is either on or off. So, it is on proportional to this voltage, and remaining time it is off. That remaining time actually depends on sawtooth period. Now, how to generate this sawtooth wave, that is to be seen. Now, there are many ways we can design the sawtooth wave. For example, one easiest thing is we are already seen the current source. So, I can have a constant current source. I can have a constant current source, put the capacitor here. So, for example, this is plus 15. So, this is current I always flowing constant. So, if I have a capacitor C, so voltage at this point will linearly rise. This I can give it to this point. So, whatever voltage, for example, I want to reach this to 10 volt and repeat. For example, I can stop this one once it reaches 10 volt. So, I can do two ways even without sensing this. For example, I can have a discharge circuit here. Here I can have a square wave generator, and it will be when a pulse comes, it will be discharging slowly. So, what it can be done is during the rise time it has to discharge. So, I can do one thing, I can put on resistance to remit the base current. So, whenever this rising wave comes, so you will have a plus voltage coming here and it will discharge, then rest of the time it will be keep charging. The next pulse comes here, the next pulse comes again at the rise time, this will discharge once and then again it will be slowly rising. So, this way the heater voltage can be on off time can be controlled. So, we can the frequency of the sawtooth is determined by this, frequency of the sawtooth is same as frequency of this square wave generator, and then this C and the current source to be selected such that within that one period one cycle, before the next expiring comes, this current source charges this C to appropriate voltage, and that actually can be found by this formula I into T is equal to C into V. So, T is the time period of this square wave generator. So, if for example, if I want 1 millisecond, T is equal to say 1 millisecond. If time period of this generator is 1 millisecond, square wave generator is 1 millisecond, then I can select I into 1 millisecond, then C, and if I want 10 volt as a peak here for sawtooth, then I can take 10 and I can select I and C. So, for example, if I fix C, automatically I can be selected. For example, C I can take 1 microfarad and then automatically I you get it, and you have to make a constant current source of that I value, that will give you the sawtooth wave here, and the sawtooth wave will be compared with the reference, and that will drive the heater on off. So, this works fine for DC supply. In case if you want a heater drive for 12 from heater tray from 230 volt AC, like if I want to use a triac and then control the heater, particularly that is very often used in high power ovens and so on. So, then using of this kind of triac is this kind of MOSFET or IGBT is not good, because you need a DC voltage. Of course, one can rectify the AC and give this. Nevertheless, if it is a triac, it is good. And then there is one more issue to be handled in this. For example, when somebody uses this, in case if the heater is short circuited, for example, some reason the user may unknowingly short this. In that case, whenever the I pulse comes here, the MOSFET will be switched on and then the MOSFET will go bad. So, we have to give some sort of short circuit protection for this, then only the circuit is useful. So, we will see how to provide a short circuit protection for the MOSFET. So, we see how to give, because we had seen earlier how to give a short circuit protection for linear power supply. The same trick can be used here. Of course, it needs a small modification, like for example, if this is the I will look only the MOSFET part alone now. So, if I take the MOSFET here, so we had this and then we had the heater there and then we had this. So, one easiest thing that can be done is that if this is high coming here, I put one resistance here. So, this is on off signal coming from the PWM stage, pulse width modulation stage. So, if the current goes high, we know that the whatever resistance I kept, that will develop a voltage across this, then I put the transistor across this, and then this collector I terminate it here. So, when the suppose if the in a normal case when the heater is on, this voltage across this will not be 0.6, it will be 0.2 or 0.3. So, that this transistor is not activated and it is not doing any part, not playing any part, and the heater works normally, that is whenever it is on, this is on, whenever this is minus or 0 volt, this is off, that will be taking place. In case if the short circuiting takes place here, then the load current is very small, then the voltage at this point will increase go more than 0.6. Once it goes more than 0.6, this transistor will conduct heavily. Of course, to protect from a spike and so on, I can add one small series resistance here. It assuming base current is small, that this resistance plays actually no part, but when high voltage spike comes you should not destroy this. So, we put on limiting resistance, that is all. Nevertheless, once it goes more than 0.6, this will conduct, and then the current whatever is coming, the voltage whatever is there, it actually divided now it conducts. So, there will be a voltage of this and the gate voltage will come down. Once gate voltage comes down, the MOSFET will enter into a linear region, that is it will be neither fully on or off, but nevertheless current will be limited by this, because you have here it is R. So, voltage across this will be R into I. So, that has to be only 0.6, because this voltage cannot go more than 0.6. So, depending upon this resistance value, the current, that much current will go, and the MOSFET resistance will be adjusted to make sure that that much current only flows. So, MOSFET quickly drawn into a linear region, but still that current, suppose if I put in this case say 0.1 ohms, then 6 ampere current will flow at 6, but 6 ampere, and this is already shorted, that is why current is going, but current will not be more than 6 amps, but 6 amps, and then about say if this voltage is 300 volt, 300 volt and 6 amps will give 1800 watt heat dissipation. So, that is 3 ampere, 6 ampere into 300 volt will be 1800 watts of heat dissipation, that will be high. So, in few microsecond this MOSFET will go into vapor state. So, it will get burned off, and it is also explodes with the vengeance. So, one should not, if you once this activated, once you short, then you will find this is exploding, and the purpose of the protection is lost. So, but what we have to do is this is acting as a current limiter. As soon as this is activated, you see that this voltage are gone to high because this is shorted, that is why the entire voltage is coming here. So, this point voltage will go up. Once this point voltage goes up, we should shut down the MOSFET. So, otherwise the MOSFET will go into the vapor state. So, one should, this is acting as a current limiter. Once current is limited, then this voltage must be sensed, because normally when the MOSFET is on and when the heater is not short circuited, the voltage across the MOSFET is very small, maximum 2 volt or 1.5 volt, or at the maximum 3 volt, not more than that. But if it is short circuited and if the current is limited, then you will see almost all the voltages across the MOSFET. So, we should sense this and then switch off the drive itself, then only the MOSFET can be protected. So, what we have to do is we have to sense this one. So, what you do is the next stage is you will sense this voltage. I can sense this by having a divider and see that what is the voltage, that if this is high compared to my reference, I put the reference here. For example, normally this will not be more than 3 volts, so I keep here 3 volt. So, if the voltage goes more than 3, the output will go high. Now, what I do is this high voltage should pull down, but that should pull down only when the gate is on. So, what I do is I will just do one more trick at this point. For example, I can have one gate here. For example, I can compare this, say a CMOS gate, and I will say apply only the plus here, then I have another input that I apply from output of the pulse here. If this is high, then what I do is if this is high, I put one small divider here, RC network. Then once this I just complete the circuit, then I pull down this completely. So, in this case what is happening is, once the pulse comes high here, this will come high and then this will switch on. In case if the heater is short circuited already, then this voltage will go high, and then this voltage will pull down to say around 5 volt, because if it pulls 0 completely, this voltage will disappear. So, it will not normally pull down, this will be sitting around 5 volt, and this will be conducting that 6 ampere current what I discussed earlier, because that depends upon 0.1 into say 0.1 ohm I have put. So, 0.1 into 6 ampere will be 0.6 volt. So, at 6 ampere current will be flowing, and that will make this voltage go high, and that if this voltage is high, this will go higher than 3 volt, that will come high, that will come high. Now, since this is high, this also already high, and this will go here. I had switch, sorry, I had to add that resistance here to protect the base. So, once this output goes high, then this transistor will conduct, and that will make this one to go to 0. That will make this one to go 0, and the MOSFET will go off. Once it goes off, there is no problem, this is still high, and then this is still high, and then this will be still high, and then we know that this also command is there, this will high, and then it will be completely latched. Now, you may ask, what is this I had done here with the RC? This is actually when this goes high first time, then we had allow this, if this no short is there, we should allow this to work. So, what happens is, if there is no short, this will go high only after some time, because initially when the MOSFET is off, this will be high. So, anyway this fellow will be high. So, this will go high after some time only. By the time this will be switched on, and once switched on this voltage, if there is no short, this voltage will be low and this will be 0 and this will not go high, it will be on. So, this will be latched permanently, that is this arrangement will protect the MOSFET once if there is a short occurs, and then if one short removed, it have to work. So, the this information, that latched information should go to the controller, so that the controller can make sure that the latch is removed frequently once in a while. So, that arrangement can be done, like for example, we can have this signal switch on off once in a while, so that if one short removed, the current conducts and then it works. So, you can think over this issue and see what best it can be done, or even this circuit can be modified such that it automatic recovery also possible. This I leave it to you as a exercise. So, this way the MOSFET can be protected. We can also design a circuit such that we can use thyristor instead of MOSFET, and till we can use the thyristor provides the power to the heater linearly with respect to error voltage. So, that design can be done like this. So, we can have a AC source and then we can have a load, and then we can have say triac or thyristors, two thyristors connected like this, and then as that we can have this. First I will do without isolation, then I can add optocoupler and connect the isolation. Here we have to switch on and off the thyristor proportional to error voltage. So, if I have a error voltage, assume that I get error voltage from this op amp, then this I have to compare it with the sawtooth wave. So, I can put a sawtooth wave here. So, that is same as what we had done in our earlier case. So, we will have a minus here, then assume that I have a sawtooth here generated at this point. For example, in this case there is no isolation. So, I connected this also to ground. We will see how to isolate next. So, I can have this, of course, I want to fire this. So, I can have plus 15 here, and then current limiting resistance to the gate of the thyristor. So, whenever this is if the error voltage is more, we know that say 2 volt, error voltage 2 volt, only when the sawtooth wave goes more than 2, output will 10 minus. So, still it reaches still the sawtooth reaches 2 volt, output will be high. If this voltage is 3, then the output will be high, still this reaches 3 volt. That means more the voltage, this will be high for more time. So, if this is high, automatically this will be high, and this is switched on and the MOSFET will be on. So, here the time constant, this sawtooth wave is a very slow wave. For example, it can be once in 0.1 second or once in 0.2 second one cycle. So, if it is say or once in 1 second, so it will take for example, if it is 5 volt and if the sawtooth wave is say 1 second wave, 1 second takes time to go 0 to 10 volt. So, this is 0, this is 10 volt, assume this takes 1 second. That means, if the error voltage is say 2 volt, then it will be on for 0.2 second on, and 0.8 second it will be off, because here is the 2 volt. So, to 10 volt it takes say 1 second. So, it goes 0.1 volt per second. So, the rate at which rising is 0.1 volt per second, the rate at which is 1 volt per second, sorry, because it takes 10 volt 10 volt per second. So, 0.1 volt per second, correct, 0.1 volt per second, that is the rate at which it is rising. So, sorry 2 volt it will reach 2 volt to reach point, okay, no sorry. So, it goes 10 volt in 1 second, So, it reaches 1 volt in 0.1 second, sorry. So, it goes 1 volt in 0.1 second. So, this rises at the rate of 1 volt per 0.1 second, that means to reach 2 volt it need 0.2 second. So, after 0.2 second only the sawtooth will reach here 2 volt. So, it takes 0.2 second reach. So, still the up to 0.2 second will be on, and several AC cycles will be going through that, because one AC cycle lasts only 20 millisecond. So, 100 millisecond only 5 cycles, and 200 millisecond you will have 10 cycles will be conducting. Then per remaining period, that is remaining 0.8 second will be off. So, if you see the pulse at this point, sorry, if you see the pulse at this point, you will have 0.2 second on, 0.8 second off. So, this will be 0.2 second and this will be 0.8 second off. So, if it is if this voltage goes to 3 volt, then it will be on for 0.3 second, off for 0.7 second. So, if it is 5 volt, it will be on for 0.5 second, off for 0.5 second. So, as the voltage increases, more time it will be on and less time it will be off. That way power that is flowing is proportional to the error voltage. This way you can use the resistor. Only drawback of this circuit is this ground must be equal to say this ground, the only current will flow through this. If you want to break this, we can add opto isolator for this circuit to make it such that there is no shock hazard. So, the same thing can be modified like this. So, I can have a AC voltage here, and then you can have the triac, you can have this, then we can have the output from the PWM stage, that drive stage. Now, instead of giving directly to this, I can connect to the opto isolators LED, that actually can be connected to the other side, which we had done earlier in the our, and that is the plus 15 volt, whose ground is this, not the ground of this. So, you have isolated plus 15 volt, that actually will drive the opto isolator. That way the isolation is provided. In this case, this ground is different from this ground, and this supply ground is same as this, not this. So, that way now you get a opto isolated PWM stage. There are still improvement possible in this, that is there are actually this is called inductor cycle control. We can also make a circuit using zero crossing detector, that also can be included. That is in the sense that now it is firing randomly, that is when it comes high immediately it is fired, but the I coming need not be coinciding with the zero crossing of this AC, because if the AC cycle, if it is like this, if I fire at this point, automatically it goes off at this point. Next cycle, since voltage is present, it is firing again like this and it goes. Suppose if the gate signal comes high at this point, then you will be firing and suddenly large current will be flowing, that produces electromagnetic interference. So, normally in this inductor cycle control, it is better firing voltage is given only at zero crossing point. If that is done, then the noise will be less. So, that circuit can be added by synchronizing with the 50 Hz AC. Again, that I leave it to you as a exercise. Zero crossing pulse with modulated firing circuit can be made for high power applications. Now, even this is available as a solid state relay in commercial market. All that you have to do is that one need not even buy this. Suppose if you have a error voltage here, all that need to be done is you have to convert into sawtooth wave, give this one the sawtooth, that I told you how to make a sawtooth wave generator. You can have this, okay, sorry, this has to be minus, then you will get a sawtooth wave here, and that actually can be given, you have a block available as a solid state relay. It is available, which contains the thyristor and all that stuff to go with that. That is your then in the other side you have this thyristor connected inside and all that firing circuit, and all the firing circuit also built in. All that you need to do is connect this. So life is little easier, one need not struggle, and you got isolation and firing circuit, everything. Whenever this is high, this will be on, and whenever this is 0, it is off, and also solid state relay with 0 crossing as well available. So you can buy solid state relay with 0 crossing. So that is, even though you give high here, this will be firing only at the next 0 crossing. It will wait still, next 0 crossing occurs. So that kind of solid state relay is also available in the market. Basically they are nothing but optocoupler combined with triac or 2 thyristors connected back to back. Added then of course the power supply requirement for this also automatically derived inside. You need not got to give a separate supply for this. So the one's life become easier. Nevertheless, as an analog circuit designer, one should know how to design these circuits, because you may be making solid state relay one day yourself. So it is essential to know how to design this any kind of analog circuit as is required. So here we had seen today that how to produce a sawtooth wave, how to compare it with the error voltage and produce a PWM signal, and once PWM signal is obtained, then how to use that to fire a triac with isolation, because we had shown how to use a triac and fire isolation. Also we had shown how to use MOSFET switch on or MOSFET switch on in PWM mode, and then how to give a protection for MOSFET from the short circuit, because if MOSFET or transistor used in the power stage, they must be protected against short circuit. If they are not protected against short circuit, then what essentially happens is one day or other somebody will be without their knowledge will be shorting the load, and the MOSFET or transistor will get destroyed. So if it is given to a user any transistor or MOSFET drive, it must be protected against short circuit. The thyristor, one good thing is the thyristor can be protected using a fuse. In fact, this is the only device in electronics that can be protected using the device. No other device can be protected using a fuse. So in case of thyristor or triac, one can give a protection with simple fuse added, and one short occurs only fuse blows, not the thyristor, if the proper fuse is put. But using fuse you cannot protect a MOSFET or IGBT or transistor. Always fuse is protected by these devices, not the other way around. So with this I will stop today. We will continue this in the next class. Thank you.